I'd like to now invite up Tennyson, who will give the next plenary presentation. She is a senior scientist at Redcastle Resources, which is a contractor for the U.S. Forest Service at the Geospatial Technology Application Center. She received her PhD in urban design and planning from the University of Washington. Her research interests are in the area of characterizing the relationship between landscape patterns, ecosystem functions, and human health. Her overarching goal is to support decision-making systems through the effective translation of the best available science to address society's most challenging problems. Sounds like people that we like supporting all the time. Her specific interests are in the area of modeling land management practices, particularly in urban areas, and assessing the effects of changes there on ecosystems. Scenario planning to support decision-making for urban planning and for maintaining ecosystem functions, and for collecting field data, particularly LiDAR, for forest inventories in urban areas. Caris has been heavily involved with the USAID SERVIR-Mekong project, where she goes out and trains people, builds capacity, and then she actually supports those severe developers once they have done the training. So we're really happy because it's like another version of scaling our work out that you've been doing in the field, and it's incredibly valuable. So please join me in welcoming Caris.
I just have to say it's been really inspiring being a part of the summit. I'm excited to share the work that we've been doing. A little bit of background in terms of like my affiliation with this project. So I work in the Geospatial Technology and Application Center with the U.S. Forest Service, and we're a Washington office, although we're based out of Salt Lake City. And we provide geospatial support for all of the U.S. Forest Service staff, including international programs. And so the international programs of the U.S. Forest Service their mission is to connect forestry staff in the U.S. Forest Service with international forestry staff or foresters working abroad and have exchange of ideas. So while I work a lot with our local, like U.S. agencies, about half of my time I've been working in Southeast Asia. And one of the projects I wanted to share with you is this project that I'm working with, the NASA SERVIR hub out of the Mekong. And we have a couple colleagues here today. They're also affiliated with the project. And it's the collaborative development of a regional land cover monitoring system. We have a big team, and I'll pay tribute to everybody on the team. Hopefully I didn't miss too many people at the end of the presentation. But so I'm with the U.S. Forest Service. We also work with SilvaCarbon, a multi-agency consortium, NASA SERVIR, and then a team out of the University of Maryland that won the ROSES Award, so Research Opportunities for Space and Earth Sciences. And so collectively, our goal is to build resilience of the community using Earth observing science and data to make better land management decisions. So the team that I work with is operating mostly in the Lower Mekong. So it's 5 countries: Cambodia, Laos, Myanmar, Thailand, and Vietnam. It has a population that's about 3/4 the population of the US, 240 million people. A lot of them making a living off of the land, so subsistence agriculture, forestry, fishing, tourism, manufacturing, and energy production are also major economic drivers in the region. It's a biodiversity hotspot, so I'm sure a lot of you may have visited Thailand and some of these regions and seen the diversity of wildlife and plant communities in the region. And it's a tropical, subtropical, and then up in northern Myanmar, temperate climate. The project started roughly 2 years ago, I believe. I have only been on the project for a year. But it was initiated by the SERVIR-Mekong, the hub working in the region. And they conducted a geospatial needs assessment with their full team of partners. And it includes government agencies, civil society organizations, and research colleagues. So they have a university consortium that they work with. And it was a fairly unanimous feedback that they needed more timely and more efficient production of land cover and land use data to help them with planning for climate change, land use management, the whole spectrum of sustainability initiatives that these regions face, any region around the world. The status and challenges that they face in updating these, important data sets, financial and staff resources, so it's expensive to maintain the hardware, to purchase the software licenses and get access to the data historically to create these land cover maps. Each region is creating their own land cover product, so they have inconsistency between the methods applied between countries, but then also from time to time, the methods are not always well documented, or they make improvements and they don't have the resources to update last year's map with the new methods. So our collective team objective, and this is like the big team of all of our partners and then our USAID funded agencies, is to support the development of a regional land cover monitoring system. So to bring all of these partners together and design a system that works to meet everybody's needs. So the much larger team developed 7 design criteria that guided this whole process. So the first is collaborative development. We wanted to make sure all stakeholders and end users were included throughout this whole process. So we developed a product that was useful to them and would actually inform policy and better actions on the ground. We wanted to make sure everything was transparent and free. The product was updated on an annual basis, had a moderate resolution. And the architecture was flexible and adaptable so that it could be updated, but it could also be tailored to meet specific agency needs. We needed to build institutional capacity to make sure that they could be fully included in the design, but then we could also rely on the network of our partners to maintain the system over time and to improve it over time. And finally, they wanted to make sure that we had assessments of the uncertainty of the product. So I know a lot of times when you make a map, it's a beautiful map and you show it to somebody and they find their house or the location where they live and they identify an error in your map. So we wanted to make sure that we had an ability to adequately communicate the uncertainty of any map product that we do create. So the first design criteria is we wanted to make sure it's a collaborative process and people are learning along the way. So this is just a snapshot of a number of the agencies and universities and civil society organizations we work with. And we brought all of these team members together through a series of 4 workshops. In the first workshop, this is where we really the teams worked to define the system architecture. So they elaborated on their own agency, end user needs and objectives. We had established a shared land cover typology. And you can imagine that each country and each agency within those countries have their own land cover needs. So it was an interesting effort to come up with a shared typology. But this also informed I think the really innovative design criteria that we're working with, which is a system architecture that is flexible and adaptable, so that even though we have a shared land cover map at the end, the system can be tailored to meet specific agency needs. So we could agree on a shared typology, but then adapt it as needed. The second design criteria addresses this need for accessible methods and softwares to create these land cover products. So Google Earth Engine, all of us are fully aware of the benefits of Google Earth Engine. It was a pretty natural fit because of the public data catalog. It's very easy to access all of the necessary imagery. We have the cloud computing power. Some of the other really powerful aspects of working with Earth Engine, especially within this region, within any region, is a lot of times your scientists, your policymakers might not know JavaScript. So the interactive, I know, crazy. The interactive map window has been really powerful to make sure that all of our partners can fully engage in this process. But they also have, we work with a full spectrum of scientists in the region, and they have a lot of really talented JavaScript programmers and scientists. So having this shared repository, we can collaboratively develop scripts remotely across country borders, across the world. So it's been a powerful platform to build this shared system. To meet the specific design criteria, we wanted a product that goes back to 2000 and is updated on an annual basis and that met the spatial and temporal frequencies to create this annual product. So we decided to start building the product with Landsat data, and then in the second version, we'll start fusing MODIS and Sentinel and other image collections into the product. So the current design is using Landsat data. And the design is flexible and adaptable. So how do we create this? When we selected and defined these 22 land cover classes, the definitions are built on these biophysical layers. So if you look at deciduous forests, we have a threshold where we determine if any pixel is a forest. So does it have this threshold of tree canopy cover? What's the phenology? So we have to have a phenology layer, the deciduous or evergreen. And then the height. So if it's a vegetated pixel, it has to be taller than, the vegetation has to be taller than 5 meters. And then we'll determine it's a forest, and it's specifically a deciduous forest class. So all of our definitions can be broken down into these biophysical layers. So in total, we have about 29 biophysical layers, which we sometimes refer to as primitives. So if you hear me use the word primitive, it's just one of these features, these map features, biophysical features that we're mapping. And they're broken up into these 5 thematic categories. So how do we build this thing with these biophysical layers? How do we merge these to get a land cover map? So we're working to create algorithms for each of those biophysical inputs. And then a lot of these are built just like with the supervised classification system, so random forests or other machine learning algorithms and reference data. We get these 27, 29 biophysical layers, and then we have an assembly algorithm that merges these into the map product. The nice thing about this configuration is you can redesign the assembly algorithm to meet agency needs. So we're working with Mekong River Commission. They have 42 land cover classes that they use in their hydrologic models. And then we also work with Myanmar Department of Forestry, and they don't need that high level of detail on all those land cover categories. So we can reconfigure this assembly algorithm to meet different end user needs. And as we have advances in methods, in data, and in processing capacities, I don't know, we can update all of our primitive products and create a new map going back into time. So we'd have like an Epic 1, version 1, version 2, version 3, but they would all be compatible across time because we can update it, all of the map products using those same methodologies. So how do we implement this? This is the capacity building piece. So we had a workshop where we got our team together, and the first workshop, we had half of the team working on the collection of reference data and half of the team working on building these primitives. So for the reference data, we wanted to make sure that we had a systematic way to update and add to our reference data collection process. So we looked at a number of platforms to collect reference data from high interpretation of high resolution imagery. And we really liked Collect Earth. But we wanted a system that was all online, so we could have simultaneous data entry. You didn't have to download any software, and all of the information was compiled on the fly in the background into the same database. So we partnered with FAO, who we have a lot of our colleagues here today, and are in the process of creating this Collect Earth online tool, and we intend to collect new data via mapathons with Collect Earth Online. But we needed to build something while we're waiting to develop this or find the development. So we also had this plan or approach where we collected legacy data. So all of these agencies have a tremendous wealth of data already. So this team compiled, crosswalked, and reformatted thousands of observations that we already had access to. So we have about 20,000 observations that we can work to create these basic primitive models with, and then update it with new data over time. So one team identified the design for the reference data collection process. The other team started working on the biophysical layer build. And this team did not include, it included some that were comfortable with JavaScript programming and Earth Engine, and some that were not. So we kicked this off with a 2-day workshop to get everybody kind of at a starting entry point. And then we went through this design over the next 3 days, where we had them break into thematic groups, review the relevant literature, summarize it, so come up with just a workflow design and start drafting the implementation. Once we had the design, my colleagues with the Geospatial Technology Application Center, we can help them modify their scripts and fully implement this with code snippets and help desk support. So through this process, we've been creating these summary sheets that fully define the land cover component that we're trying to map, review the relevant literature, give a review of the different methods utilized that have proven to get good results, and then we can script up a couple of those methodologies and include that as a link, so that include a script, Earth Engine script, in these summary sheets that includes both the script, so that if people wanted to modify the models we've created, and we have hundreds of covariates they can choose from in any random forest model, so they could see the output and they might think, oh, you shouldn't use this NDVI layer, use this vegetation metric. They can swap things in and out and rerun it and compare it to our best product. If you don't want to dive into the methods, into the models, it's a good way to just show our partners what the products look like and identify where there's data holes. So when we first started collecting reference data, we had maybe 1,000 observations, and through these summary sheets, we started getting a lot more reference data. People in Cambodia realized on the first summary sheet, we haven't shared any of our data with you. So we started getting data from Cambodia and really started filling in these holes through the communication of the process. But we assess uncertainty through capturing pixel level probabilities based on the votes from machine learning algorithms. So we can communicate this uncertainty when we share our map products. And then when we combine all these biophysical layers, we know that each of our map products have a level or a bit of uncertainty associated with all of the predictions. And if we combine these products with kind of a static decision rule set, we lose a lot of the information about the uncertainty. So we use Monte Carlo simulation during the assembly algorithm process to propagate the uncertainty associated with each of our data products into the final land cover product. So the fourth workshop is this August, and this is where we work with our end user cases again, and we've identified 3 agencies we'll work with to tailor the system to meet their specific needs. So we'll be working with the Myanmar Forestry Department to update their forest monitoring map, the National Institute of Agricultural Planning and Projection in Vietnam to update their rice maps to get more information for their agricultural insurance programs, and the Mekong River Commission. They have some hydrology models that we'll be using. The land cover information will be fed through the hydrology models for their decision support network products. So my closing reflections, I'll just wrap it up with 3 things. The power of Earth Engine to collaborate has been really wonderful to work with, to share our data products, to share our data input, so help visualize Landsat data, collect reference data, and then also refine all of our algorithms. When you're working with a really diverse team, you got to get creative. So one example of just being impressed with the creativity of our team as you can imagine, different agencies want to keep their data private. So we had to get creative in how we shared data to train some of these models. So a number of countries gave us their land cover and land use maps and generated random points within that we could do a QA, QC on. And that's our reference data. So we didn't use their specific reference data, but they helped us find a set that protected the privacy of their data, their raw data. And then, just to wrap it up, it's a non-traditional process. It takes a bit longer to do the collaborative development. But I think it's pretty valuable to make these connections across country borders, to share information and exchange ideas. So I think, without further ado, I'll introduce the full team. And as I was sitting at breakfast, I was like, I forgot. I forgot a couple people, but I didn't have time to add them in. So apologies if you noticed that I'm missing people. So thank you, everybody. And if you have any questions, I'd be happy to take them if we have time now or throughout the day.
Yes, we definitely have time for a few questions. I would just start by saying that was an awesome illustration of the point of, like, once a tool comes out, like Luis was talking about, there is so much more work you get to do, creative work, that wasn't possible before because you never got through the busy work of, like, assembling all the data. And this is just a great example of, enabling, like, a whole new higher level work, basically, that can be done because of the underlying tool of Earth Engine. But Earth Engine is just like a small core of this huge project. And that coordination is impressive that you're doing.
Thank you, Dr. Karsh. This is amazing. I'm Tasfai from World Resource Institute.
Yeah.
I have one question. So you create these massive products, and I'm wondering if it is actually feasible for revisiting, like monitoring of the biophysical aspects, also the socioeconomics and the governance-related stuff. Like if things are changing, is there a way actually kind of use as a monitoring tool?
So you're asking about, like, assessing the impact of the data products? Yeah, so the SERVIR-Mekong team that works there regionally works with these partners, and we'll follow up with success stories, like how is this product making an impact? So we're still in the development of the product, so it's a little early to say the map product made much of an impact, but we already see that the process has made an impact. Just a couple of the university professors that we work with in Vietnam, they're really active on the developers forum, and I see projects that they're kicking off using Earth Engine and a lot of the stuff that we've been working with them on. So I know they're implementing some of the work we've been doing to build capacity to process this data is being utilized in the region. Yeah.
Hi, thank you. That was a really great presentation. I was curious if you could just comment quickly on, my group works on marine applications, and particularly we're looking at aquaculture. And I know one of the troubles with mangroves in that part of the world is their conversion to shrimp ponds or other forms of aquaculture, which can be difficult to classify when you're looking at more terrestrial land cover. So I was just curious if you guys address that issue, or if that's how you went about that.
We went about that by working with thematic specialists. So I personally can't speak to how we're addressing that, but I think that's the value in breaking out the map creation product by these biophysical layers is that we can work with these domain specialists. So we have a number of both cropland mappers that we work with, and also mangrove specialists. So I feel like that building that network and that communication vehicle between those domain experts assists them do their work. So good question.
Thanks. So I'm interested, you said in the crowdsourcing aspect, and I just want to know the tool that you used, did that play directly with Earth Engine, or did that avoid problems of duplication, the same people looking at the same, or different people looking at the same spot? Can you talk a little bit about that? Because as Luis was saying previously, that's often the bottleneck in these machine learning processes, the training aspect.
Yeah. So I want to say in November, we spec'd it out. and got a grant to develop Collect Earth Online. So it's available right now in a beta version, but a lot of those functionalities that you talked about will be built out into the final version. It has some of it already. So right now you can document, it keeps track of who your data users, who's entering the data. And so it started off as a SERVIR-Mekong tool that was called MAPTCHA. And the MAPTCHA version, we wanted to make sure we could do some QA, QC between people entering data. And so it also had this, in the background, people didn't realize it, but everybody was being randomly assigned points, and each point would be assigned to up to 3 people until we got an agreement of, kind of an agreement of land cover classification from these observers. We turned it off in Collect Earth Online right now, and we're testing a different process, but I do have to say, when we've been creating some of these primitive layers, or the summary sheets, I wanted to include an accuracy assessment. So like just your standard confusion matrix in the end of all of these to assess how we've done quantitatively. So I set up a project on Collect Earth Online, and I farmed it out to our team, and then just some people that I work with at GTAC and friends of people that we work with at GTAC. We collected 600 data points really fast, and I ran through our numbers. I was like, wow, this primitive is horrible. Like, our models do not work. And then I looked at the models. I was like, they seem okay. So I went back to the reference data, and somebody entering data maybe didn't understand the definition of croplands compared to how we were defining them. So we had to go back and do some QA, QC on this crowdsourcing method. So we're definitely learning as we're going. Yeah. And refining to make a better product. So if you have questions, I'd love to talk to you more about ideas afterwards. Yeah.
Thank you, Chris.
Yeah.